Welcome again in our third video, which is about significant figures. So, I will not be discussing all of the rules because you already have your handout, which is very comprehensive and has more problems, but I will be just tackling significant figures through some very basic problems that will be used in our topic. So, as you can see, based on definition, significant figures are digits that represent reliable or known digits in a number or a set of numbers in measurements and computations. And it is very useful in a lot of fields of sciences like physics, chemistry, of course, engineering, and a lot more. So let us try some problems, three very basic problems that we can be used to to learn this concept. So the first one is we need to identify the number of significant figures, and the last two is to do the operations and following the rules of significant figures. So first is 0.003048. So first, the very first trick that I always use in identifying the number of significant figures is identify first all non-zero digits. So we have 3, 4, and 8, meaning we already have 3 significant figures. Next is identify all zeros between those non-zero digits. So we have 1 0 there, and we will add it immediately. So we already have 4 significant figures. Next is if we see zeros before or on the left hand side of the leftmost significant figure, it is considered not significant. If there is a decimal here or I, within these 4 digits, all zeros after that will be significant. The only thing that is not significant are in the left side. But if it is on the right side of a decimal, it is considered significant. Since there are no zeros here, but there are zeros here, these are not significant. Thus, our final answer is that we have 4 significant figures. Next, let us perform this computation, and I am highly suggesting you already computed it in your scientific calculator. So we have 36.01 minus 0.4 minus 15. So our answer is 20.61. Next, we will now identify the rule that is related to this computation. So according to one rule in significant figures is that when we are dealing of subtraction or addition, we need to take note the number of decimal places. So we have 15 having 0 decimal place, 0.4 having 1 decimal place, and 36.01 having 2 decimal places. So based on the rule, we need to identify the number with the least number of decimal places, and afterwards that will be our basis on our final answer. So since zero decimal place is the very least, meaning that our answer should have no decimal places, have zero decimal places. If the very least is 1, or the least number of decimal places is 1, then we should have an answer with 1 decimal place. Since it is 0, then we need to disregard this, but remember to round off if needed. So since it is 6, it is greater than 5, meaning we need to round the number off. Thus, our final answer is 21. Lastly, so again, let us already compute the number 0.03 times 98.1, which is 2.943. So how can we identify the correct number or correct final answer? So similar to the addition and subtraction, in division and multiplication, we need to identify not the decimal place, but rather the number of significant figures. So we can see, or as we can remember, 0.03, these two zeros are not significant, thus it only has one significant figure. Lastly, 98.1 has three significant figures because those three are non-zero digits. Thus, we need to again choose the very least or the least number of significant figure, just like in the least number of decimal places. And then that should be the final answer. Also, again, remember to round off. Since 9 is greater than 1, we need to add 1. Greater than 5 rather, we need to add 1 to 2. So our final answer is 3. Since this leftmost should be the very first significant figure. So we are already done on significant figures. I hope you can be familiarized with these rules so that we can um, be mastering. We are mastered now with significant figures. Proceeding to after significant figures, we will now be tackling about measurements. But what are we going to measure? So first, we will be tackling about the properties of matter, as by definition of chemistry, it is part of chemistry. We need to identify the properties of matter. So the properties can be physical, chemical, or a particulate nature. As we tackled already on the on states of matter, particulate nature is actually the structure, the atomic, the subatomic, and also the quantum properties of a substance. Physical properties are properties that can be changed without changing its composition. One example is um, the properties of water when it changes from liquid to solid, solid to liquid, liquid to gas. So it has different properties. Liquid water has different properties from ice, has different properties from um, water vapor, but they are all water. They are all H2O. So it the density of water or H2O itself is a physical property as an example. Chemical properties, on the other hand, will have a very different or either a slightly or very different property when it changes from when we change rather the composition. For example, when we are cooking a pancake, so it turns from liquid to solid, but as we can see, there are parts that somewhat burn. So meaning there is a combustion reaction within it or a caramelization within it. Thus, there will be a formation of a new substance, meaning there will be changes in the composition of the substances. So, what is the, or rather, there are also subdivisions of physical and chemical properties, namely either intrinsic or extrinsic, intensive or extensive. They are both the same: intrinsic, intensive, extrinsic, extensive. It only differs on the definition. Intensive or intrinsic properties means that the property will not change even if you add or remove some amount of matter within that substance. For example, density. Even if the density of water, no matter how much water you put in it, it still has 1,000 kilogram per meter cubic meter density. On the other hand, extensive or extensive properties are properties that will change depending on the amount of matter. For example, is mass. When we add more clay on one clay, it will have more mass. It will have more weight, meaning it is extensive property. So, why am I tackling about properties of matter? Because these properties of matter will not be, we are measuring these properties of matter. It is the very basic of measurements. We are measurement properties of matter are physical quantities that can be measured. So, how can we write these measurements without writing the name itself? So, for example, I want to say that this number is density, but I don't want to write density and then the number. For example, in calculations, you cannot write density, density, density all over throughout the calculation. It will consume space, time, and effort. So, these were the units came from. So, we have, in our generation, in our time right now, we only have, or rather, we have two unit systems that are most commonly used, namely System International d'Unités, or the SI, or the International System of Units, and also the United States Customary System, or USCS. So the only difference are some values when we are converting from one system, one unit system to another, and also the names. For example, in SI unit we use kilograms. In USCS we use pounds, and so on. So the SI is also known as the metric system, and the USCS is also known as the English system. So, as you can see in this table, I am these are also known as the fundamental quantities. What are fundamental quantities? From the name, or from the word fundamental, meaning the very basic. These are um, quantities that do not have origins or do not have derivations. They are the reason, or they are the main cause of derivation of other quantities. Without one of them, a lot of derived quantities will be vanished from science. So we have length, mass, time, electric current, temperature, amount of substance, and luminous intensity. So these are its SI base unit and its name. So as you can see, these are some commonly used derived quantities in chemistry. So for example, volume. Volume is actually derived because you are just multiplying three lengths. One length times one length times one length. So we have three lengths. So meter cube, cubic meter. Density is just the ratio of mass and volume. Pressure is just the ratio of force and area, and so on. So we have energy, molar mass, specific quantity. capacity, ionization energy, concentration, enthalpy, and entropy. So moving on, we will be also using or dealing with more mathematical concepts like the prefixes that we will be tackling more on scientific notation and dimensional analysis. So scientific notation is actually another way or a method of expressing numbers, measurements, especially when they are very large or very little. Like the Avogadro number, it is written always in scientific notation because it is it has a base of negative and an exponent of negative 23, which is a very very small one. I mean positive rather, which is a very large number if we think about it. So these are the steps on um, how can we change a number into scientific notation format. So these were the prefixes came or come in hand. So just like in mostly you can hear it in a lot of ways. Like instead of grams, we commonly hear kilograms. Instead of meter, we sometimes hear centimeter, millimeter, nanometer, and so on. So these are actually the basis. So they have multiplication factors regarding the very basic. For example, meter. So 1 kilometer is just actually 1,000 meter. 1 millimeter is actually 0.001 meter. 1 centimeter is just 0.01 meter, and so on. So we can actually convert this by using or by changing the prefix of the units. So instead of moles, we can use teramoles, gigamoles, megamoles, depending on what is needed. So again, we will be using more of a example based learning on scientific notation because it is a more technical or practical um, skill that we need rather than just memorizing the steps. So first we have two examples here, 19,300 meters and 0.00012 seconds. We want this to be in scientific notation format. So how can we do it in scientific notation? So first is we need to if the given does not give you a number of significant figures needed or decimal places they wanted or units they wanted, like if they just want 19.0 19.3 as the coefficient, then you need to have somewhat a very different approach, but they are just the same rules or same steps rather. So if they do not, if the problem does not give you a given on how will you write the coefficient, then the very first step you need to identify is the leftmost non-zero digit. So we have here 1. And then we will put, so we know that there's a decimal place here. We need to travel this decimal place to the right side of 1. So we need 1, 2, 3, 4. So this is 1.93. That is our A. That is our A. 1.93. Then remember this distance. We need, so as you can remember, I counted 4 steps. 4 steps. So based on the rule or the steps, if this will be our P, and if P travels from right to left, B is positive. From left to right, B is negative. So our B is positive because it traveled from right to left. So we will just substitute it in our format. So which is A times 10 raised to B. So our scientific notation is 1.93 times 10 raised to B, or raised to 4 meters. Let's not forget the units. So that is our final answer. So let's now proceed to a very little number. So again, let's find the leftmost non-zero digit, which is 1 again. And then put a decimal place. There we go. So A is 1.2. Next, remember this one. So 1, 2, 3, 4. So it traveled again 4 units. So B is equal to, is it positive or negative? So based on definition or based on the method, if the decimal place traveled from left to right, meaning it should be negative. So our B is actually negative. So substituting it again in our format, so it should be 1.2 times 10 raised to negative 4. So that is our final answer, but let's not forget the unit, which is seconds. So later on, we will be tackling about dimensional analysis, and let's try to convert this into another form by changing the prefix of the unit. So you may now proceed on the last video.